GATE is a competitive examination attempted by over 1 million students every year in India. This is a February 2016 paper in Computer Science and Information Technology. We are dealing with the question and the theory of computation. GATE is used for entry to higher education and also for government jobs in India. Here is the problem, question 43 in the Computer Science and IT paper. Consider the following languages. In the syllabus, we know languages may be formal languages in the Chomsky hierarchy. There are the languages L1 and L2. We are given this language or this language. We are asked to find out if both L1 and L2 are context-free, or L1 is context-free and L2 is not, or L2 is context-free and L1 is not, or neither L1 nor L2 is context-free. Let us study the languages. L1 says A's followed by B's followed by C's. A's come first, B's come next, C's come at the end. The number of A's is n, number of B's is n. Number of A's plus number of B's n plus n is the number of C's. So number of C's equals number of A's plus B's. But remember, A's come first, B's come next, C's come at the end. And M and N can be greater than or equal to 1. So at least one or more A's, one or more B's, one or more C's. Let us consider L2. L2 contains A's followed by B's followed by C's. N is greater than or equal to 1. So at least 1A, 1B, 1C. A's come first in A's. Equal number of B's come. Then C's come at the end. Number of C's equal number of A's plus the number of B's. Now, we have to study these languages and decide whether which one is context-free and which one is not context-free. Let us consider the case of the language L1. We claim L1 is a language which is a context-free language. How do we justify the L1 is context-free? There are two ways. Either we construct a context-free grammar generating L1, or we design a push-down automata which will accept L1. We shall do both methods. So how do we claim L1 is a context-free language? Method 1. We will construct a context-free grammar, abbreviated CFT, to generate the language. Consider this grammar. There are productions 1, 2, 3, 4 productions. S goes to AC or S1, and S1 goes to BS1C or epsilon. The non-terminals are S and S1. The terminals are A, B, and C. Epsilon is empty string. We claim this grammar generates L1. How do we do this? Well, look at the first rule. S is here, S is on the left-hand side and right-hand side. So as I apply the first rule, A's are pumped on the left-hand side. Equal number of C's are pumped on the right-hand side. These give me the initial A's and the final C's at the rightmost part of the string. Then S goes to S1. The second step, B's are pumped after A's. Immediately C's are pumped after that. Whenever A comes, the C will come. Whenever B comes, the C will come. The number of A's to the number of B's is equal to number of C's. Number of A's are independent to number of B's. We can pump this first rule as many times as we want, independently of the second one. So this grammar in effect generates L1. This is a context-free grammar. Why? Left-hand side of each rule is single non-terminal. So the context-free grammar, so in effect L1 is a context-free language. Another way we can justify L1 as a context-free language to construct a push-down automata PDA to accept the language, context-free language. This is what we do. We construct a push-down automata as follows. Push-down automata will have a stack. It reads the input left to right. It pushes the A's onto the stack, then pushes the B's onto the stack, checking that the B's come after A's. Then when C's come, it unstacks the A's and B's. Once C comes, A and B cannot come. The push-down automata can easily check that A's come first, B's come next, C's come at the end. If at the end the stack is empty, then the A plus B's are equal to C's. Push-down automata accepts. So L1 is a context-free language because it's accepted by push-down automata. So L1 is accepted by push-down automata, it's generated by context-free grammar. So L1 is a context-free language. So now we can take the problem. L1 is a context-free language. The choice is C which says L1 is not context-free. L1 is not context-free cannot be correct. Choices A and B are ruled out. You have to choose between choices A and B. L1 is context-free. Now it depends on L2 whether we choose choice A or choice B. Now let's consider L2. L2 says the number of A's was equal to the number of B's, and the number of C's was equal to A's plus B's. The standard context-sensitive language that's not a context-free language. How do we know this? To show that L2 cannot be a context-free language, we will use the pumping lemma of context-free languages. The pumping lemma allows us to pump on two parts of the string. And when we pump on two parts of the string, they must be in lockstep. But L2 wants A's and B's and C's, three parts of the string to be in lockstep. When I take a very long string, A's and B's can increase, but C's will not increase. Or B's and C's will increase, A's will not increase. Or A's and C's will increase, B's will not increase. So all three cannot be in lockstep. So L2 is not a context-free language. It of course shows context-sensitive, constructing a context-sensitive grammar, generating it, or a linear bounded automata accepting it. So L2 is not a context-free language. Coming to our problem, we have L2 is a context-free language. The choice is not a context-free language. The error here. This rules out choices A, C, and D. So L1 is a context-free language, L2 is not a context-free language. This is an error over here. So L1 is a context-free language, L2 is not a context-free language. So elimination, the answer is D. End of the presentation. Thank you for the attention.